Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series, and I am delighted to have Sinclaire Jones with us today. Hello, Sinclaire.
Thanks for having me.
Well, it's really nice of you to be able to talk about your very awesome article, which we'll get to here very shortly. And Sinclaire, what's your geolocation? Where are you at?
I am in Columbus, Ohio. I am a student at the Ohio State. They're very particular about the
They
the.
are about that, duh. I think it's even like copyrighted or something like that. Like you have to say the pretty awesome. Let's see, and it is May 12th of 2025 as we record this. And is Ohio, Columbus getting a little hints of summer, or are we still sort of in our spring mode?
Ohio,
Or winter mode, as it may be.
it's weather. Yeah, so I think we pretty much skipped spring, just went straight into summer,
Okay.
went backwards back into spring. So we've had a lot of rain, but I think we're getting into summer part two again. So
All right.
it is what it is.
Let's see, and I'm in Phoenix, and we are definitely hitting our summer mode. We hit our first triple digits about 2 weeks ago, and yeah, we are
Oh, wow.
running it pretty good. So it's all good. Sinclair, where are you in your trajectory as a grad student?
Yeah, so I'm just wrapping up my third year at Ohio State in the astronomy department. Yeah.
Well, let me be the first then, since so you're all but dissertation, right?
No, I still do have candidacy. That's my very next step.
Well,
So,
yes, yes, yeah. So, I will be the first then to say, well, congratulations, Dr. Jones.
a little premature, but
Yeah, but it sounds
appreciate.
good. It sounds good. Very cool. And one more thing before we really roll. You got some interesting photos or images over your head. Did you make those or?
So yeah, these are actually just posters about some of my favorite media. In the
Cool.
center, we have my favorite movie, Back to the Future.
Yep.
Um, Over here we have Space Jam, which I absolutely love, and it's like
Okay.
a staple for my family. I know the whole soundtrack. And then we have this is Cowboy Bebop. It's a
Okay.
space jazz anime,
Okay.
so
That one I'm not familiar with. I'll have to check that out. Pretty
it's a
cool.
lot of fun.
Pretty cool. Very nice. And Sinclair, what do you like to do for research?
Yeah, so currently I'm working with my advisor, Scott Gowdy, and we are doing solar system analog study in preparation for the Roman Space Telescope and its microlensing exoplanet survey. So
Cool.
I'm just going to be estimating kind of the yield of what we might see with solar system analogs.
Cool. Very nice. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. TOI 215b, a warm Neptune with transit timing variations orbiting an active mid-type M dwarf. And Sinclair, take us away.
Yes, so as you mentioned, I will be introducing you all to TOI 2015b, which has been my beautiful problem child, warm Neptune with a period of 3.35 days. It's orbiting a nearby M4 star, and the most interesting and also unexpected part of this project was the large transit timing variations that it has. It's an amplitude of about 100 minutes, and it gave us a lot of trouble, but it made for a very exciting system.
Very cool.
Yeah, and before we really get into the science, I just want to acknowledge that this project is actually a result of my undergraduate work.
Hmm.
So, I was an astrophysics major at Princeton University, and I worked with my advisor, everyone calls him Gumi Stefansson, for
Okay.
4 years, and 3 of those years were spent on this project.
Nice.
Um, but even though I was a student at Princeton, the work I did on this project and several others were actually with the HPF team at Penn State. So HPF is the Habitable Zone Planet Finder. It's a near-infrared spectrograph that I'll talk more about later. But yeah, the team is led by Suvrath Mahadevan,
Hmm.
and many of the names that you see here as the collaborators are members of the group. They were really just so kind to me and being mentors, especially as an undergraduate. I was still learning the ropes. some of the other names as well, where people who helped collect data, run models, and those things, and everyone really helped us to piece together this challenging system. And especially my advisor, Gumi, he remained steadfast and supported the project even when things were looking a bit unsure. So very
Yes.
grateful for
Yes.
these
A
co-authors.
little stick to itness, yeah.
Yeah.
Very cool. Very cool. Good shout out, by the way. Good shout out. Okay, let's roll.
Yeah, so I guess in the introduction, I can start telling you about M-dwarfs. The reason why M-dwarfs are exciting is because they make for great targets to detect small rocky planets. So, especially with instruments like TESS and HPF that are more sensitive to redder wavelengths,
Mhm.
it allows us to do some detailed characterization of these kinds of systems.
Mhm.
Yeah, I think just then moving on to the fact that I mentioned TOI 2015 is a TTV system, and that was kind of the big mystery of this project.
Okay.
Just to explain a little bit about what TTVs or transit timing variations are.
Yes.
Um, Most planets have a very regular period. We're expecting them to transit the same time every orbit. But
Yep.
with TTVs, the transit timing is varied. So sometimes the actual transit occurs a little bit before or a little bit after when we would expect based on its period.
Okay.
But yeah, TTV systems are really interesting because what they do is let us know that there's a potential companion that's another additional planet that could be in the system. And the gravitational pull of that object is what's causing the timing variations that we see. Also, TTVs can be used to
Yeah.
constrain measurements like planet mass independent of radial velocity measurements and things like that.
Nice. Nice. Okay.
And regarding TTV systems that are around M-dwarf hosts, there aren't many, only about 10 or so. So that makes TOI 2015 a super valuable target and
Yeah.
interesting to get into.
Yeah. Of course, Trappist one, yes. Mm.
All of that.
Yeah. Cool.
Um, but yeah, I think getting into the data, we can scroll to figure one.
Okay. Stick those numbers in your head, people. A period of about 3, distance 47. Okay, figure one. Test photometry. Woo.
Yes, so this is a test object. We had access to two sectors of test data at the time. We identified 8 transits in the first sector, sector 24, and 2 years later, in sector 51, there were 4 additional transits that we identified. One really interesting thing that you can see in panel A is that there's a lot of out of transit variability because this is a very active star.
Okay. Okay. Right.
Yeah. Looking into, I guess, the next figure,
Right.
um, it'll just be some imaging
Mm-hmm.
that basically shows that the signals that we're seeing are coming from TOI 2015 and not from another nearby star that could be contaminating the signal.
Yeah.
So here in figure two, we have seeing limited images. On the left, we have an image from 1954. On the right, an image from 2021.
Cool.
The white lines that you see are
Yes.
just the test aperture, and the yellow circle is the location of where TOI 2015 is.
Very nice.
Um, Basically, all this shows us that there are no other nearby objects that could cause dilution or lead to false positives.
Okay.
Um,
Okay.
and likewise, in figure three,
Geez, that's tests. Okay. And
have some high contrast imaging.
ew, nice.
Um, yeah, this just kind of shows the same things in the inset images. You have TOI 2015, and what the corresponding plot is showing is that there are no companions that would cause contamination. And the signal that we're seeing is actually from TOI 2015.
I'm with you. Mm-hmm. Cool.
So I think then in terms of RVs,
Wow.
we can talk a little bit about HPF. Um, there were 37 RV points that we collected with HPF over a baseline of about a year and 9 months.
Okay.
HPF is a near-infrared spectrograph on the 10-meter Hobby-Eberly telescope at McDonald Observatory in
Mhm.
Texas.
Yep.
And the HPF team actually does tests, like a test follow-up survey. So they've been able to characterize a lot of transiting M-dwarf systems with this instrument. And the HPF spectra have also been super helpful for driving accurate stellar parameters, which is a
Mm,
requirement in order to get the accurate and precise planetary parameters that we need.
very cool. What do you get down to? 30 centimeters a second. Pretty good. Mm-hmm.
Yeah.
Mm-hmm. Nice. Okay.
And I guess the next thing would be the ground-based transits.
Okay.
So getting into that, we had several instruments and transits that we had access to. First, I think on the next page is LCOGT.
Mm-hmm. Indeed.
Yes. So yeah, that's a 1 meter telescope at their South Africa site. We reduced the photometry there of a partial transit that we were able to access from the LCOGT archive.
Okay.
Um, the next two transits that we got were from our amazing collaborators in Wyoming who helped us get photometry. There
Nice.
was the WIRO 2.3-meter telescope
Mm-hmm.
and also the RBO 0.6-meter telescope.
Okay. Yep.
Um, and with both of those, we were able to get full transits. So yeah, that was super helpful to us.
Very helpful. Beautiful. Okay.
And I guess the last kind of photometry that we got from the ground was with the ARC 3.5-meter telescope.
Mm-hmm.
And I will say that this was a crazy 2 weeks of observations. I led these observations myself. I had actually done my observing training back in 2021, but with COVID and everything, it was over Zoom. So
Ah.
like she was
Okay.
actually showing us like the laptop, like
Yeah.
trying to show us the telescope. It was crazy.
Oh, that's
Um,
cool.
but
Okay.
yeah, the two observations in this paper are from April 23rd and May 3rd of 2023. And I had
Mhm.
led many observing nights of this target before then. And even before I was certified, I had led many observing nights for this target. So we had an awesome observing team.
Very
I
cool.
observed a lot with Gumi. Also, there was Jessica Libby Roberts,
Okay.
Caleb Kanyas,
Good.
Shubham Kanodia, Andrea Lynn. And also Luke Powers was the other person that I got certified with on Zoom for this telescope. So we had a lot of fun with these observing nights, but we
Awesome.
also did have a lot of challenges. So
Yeah.
for like 2 years before we ever got these two successful transits, we were seeing nothing. At first it was non-detections
Uh,
because we hadn't realized yet that it was a TTV system.
okay.
And
Right.
things were transiting hours before or after when we would expect it to transit.
Right. Right.
But then when we eventually did figure out the TTVs and updated the ephemeris accordingly, then we were blessed with bad weather and clouds.
Of course. Of course.
There was even this one time where we had like a massive flare that jumped like a full magnitude in the G band, but
Mhm.
like it conveniently happened exactly when we would expect the transit to have occurred. So it was another no data night.
Thank you, Flair. Thank you, Flair.
Yeah. But these two consecutive observations, they were both successful, both full transits. We were literally talking about like, oh my goodness, the curse has been lifted. Like I'm pretty sure you could see that back in our email chain. We were talking about that. So
Perseverance
it
pays off, yeah?
indeed. So yeah, that's all
That's awesome.
the data we collected.
Okay.
Um, yeah, getting into the stellar characterization part,
Okay.
I think table one has all the parameters
Okay, let's
kind
see.
of shown together.
And
Yeah.
let's blow that up a little bit and we'll roll down the table as need be. Okay. Still at
Yeah.
print. Here we go.
So I guess the other major part of my undergraduate research was also working with HPF spec match,
Mm-hmm.
which was an empirical spectral matching code. Basically, how that works is we have a library of 166 stars with well-known parameters.
Okay.
Um, we have HPF spectra for all of these targets, and the code takes a target spectrum as a FITS file as input
Okay.
and compares it to the library of stellar spectra with a two-step chi-squared process. And the output is stellar parameters that we calculate using a weighted average of the best fitting stars and their parameters.
I'm with you.
So I think in the table you can see that under spectroscopic parameters from HPXF spec match,
Mm-hmm.
what we get are effective temperature, metallicity, and surface gravity from that.
Yes.
Also a V sin I estimate. Um,
Good.
yeah, and then those parameters actually go into the SED for input parameters for that.
Mm-hmm.
Um,
Figure. Okay, good.
yeah, and Caleb was really awesome in helping us
Okay.
work through that. I guess the next thing
Okay.
will be about um,
Wow.
TY 2015 being a fully convective star. I think you'll see it in
Okay.
right above section 3.3.
Mm-hmm. Let's take it right above there. Spectral. Do, 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 do. Yep, yep. Okay.
Um,
But
actually,
I will certainly believe that an M4 dwarf is fully convective. Let's put it that way.
yes. So you can actually see
But so you're
actually
not in that regime where, it may be a partial convection, right, a little bit lower on them. So yeah, we're in the fully convective regime.
exactly. Actually, figure four is a good
Okay.
illustration of that. This
Ah,
was contributed
yes.
by Shubham. Yeah.
Uh-huh.
So basically, what this is showing, the red dashed line is the transition between partially and fully convective. Um, and TY 2015 is at the bottom there in the fully convective zone.
Yep.
So, ta-da, we have it. Um,
Cool.
I
Very
guess the next figure, figure five,
okay. Figure five.
um,
Spectroscopy. Figure ZTF photometry. Okay, and test. Let's zoom out to get the whole thing. Okay.
yeah. So this gets us talking about this activity that I mentioned. So we have ZTF photometry and test photometry here. On the left is, I guess the left column is photometry, and the right column is the corresponding periodograms.
Cool.
So from these, we recover a rotation period of about 8.7 days.
Okay.
That's indicated by the vertical red lines on the right-hand side.
Yes.
Um,
Uh-huh.
and this is consistent in all three of the ZTF filters that we see, and also in test sector 24. But you'll notice at the
Hmm.
bottom in the J panel
Yes.
that sector 51 actually has a different rotation period, which
Yeah.
we basically attribute to sparse data coverage. And I
Uh,
mean, the one
yeah.
cool thing we do have
Yeah.
is there's a little flare there that you can see in
Yep.
the inset.
Yep.
So yeah, it's still a great illustration of the activity that we have going on.
Okay. One question. What are the dashed horizontal lines in B through F? What are those marked?
Okay, so the horizontal
Oh,
lines
there it
are
is. Percent.
false alarm
Yeah, yeah.
probabilities.
Okay.
So yeah, just because all of these kind of fall above, the peaks fall above the false alarm probability line, we know that we trust the period to be 8.7 days. So
One day I'll learn how to read plots correctly. Okay. Or completely, I should say. Okay, I'm with you. ZTF's looking good. A little sparse there on TEF on this one, but okay. Cool.
yeah, I think the next plot is figure 6.
Okay, joint fit, RV fit. And here we go with the periodogram.
Oh,
Blow that up.
lovely, more periodograms.
There you go.
Um,
Right, so I'm gonna have to zoom in a little bit to get it all. Okay.
yeah, but basically this figure, and there's more in-depth information in a table in the appendix about this. But what this shows is HPF RVs and HPF activity indicators.
Okay.
So the periodogram in the first panel is for the HPF RVs,
Mm-hmm.
and the periodograms in the subsequent panels are HPF activity indicators.
Okay.
And I guess what we see here, the gray horizontal lines are the false alarm probabilities.
Yes.
The red vertical lines are the planet orbit period, and the blue vertical lines are the stellar rotation period.
Okay.
And ultimately, kind of the takeaway of this plot is that there are no significant peaks or any significant periodicity here that would basically indicate that stellar activity is the dominant signal in our RVs. So this just shows us that for our level of precision, stellar activity is not the dominant signal here.
Right.
Um,
Cool.
yeah.
Good check. Good check. Good check.
So I think overall that gives us the stellar parameters. And now that we know that our stellar parameters are accurate and precise, we can move on to finding accurate and precise planetary parameters.
Okay.
So
Yeah.
yeah, I guess in the planet characterization, at the start of section 4.
Okay. There's our one equation. One equation. Start of section 4. Did I blow by it?
Oh, I think so. It's a bit up, I
Okay.
think.
Sorry. Section 4. Oh, yeah. Yeah. Okay. Duh. Okay. Sorry.
Yeah, so basically we still have this remaining question of yes, we have TOI 2015b, but there also might be another mysterious companion.
Could be.
So the best way to test this is by doing a transit least squares search through the test data. And we can see that in figure 7.
Okay, we get this. Boom, bump, bump. Okay, I'm good there. Figure 7. There's our photometry. There's our periodogram. And 7, least squares fit. Here we go. Okay.
Yeah, so what these are just TLS signal detection efficiency power spectra.
Mhm.
The top two panels are just a first pass with TLS through all of the test data.
Okay.
And what we see is that the period of 3.35 days of TOI 2015 stands out, or
Yes.
TOI 2015b, which is what we expect.
Okay.
But if we're looking to see if there is another transiting object that could be there,
Yes.
then we can mask out the signal and then do another TLS.
Right. Residuals.
So
Uh-huh.
that is what you see in the bottom two panels in
Got
C
it.
and D.
Got it. Okay.
Um, and basically, with the false alarm probability of 0.1%, none of the peaks fall above the false alarm probability line. And it basically tells us that there aren't any significant peaks and that we're not detecting another transiting companion in the test data.
There's no TOI 15C.
So, basically, with the information we know there, we can start doing models assuming just a single transiting planet.
Yes.
Yes. So, yeah, combining all the transit photometry and the RVs, we can run a joint fit to find the best fitting parameters for TOI 2015b.
Yes.
And if we scroll to figure 8,
Okay.
I think we can see the photometry from the joint fit.
Ooh. Yeah.
Yeah.
Nice.
So what we did is we ran a joint photometry and RV fit with TTVs. The software that we used was called Juliet. It uses nested sampling to determine parameters. And basically what we input into the code is priors on stellar and planetary parameters, including a Gaussian process to model out the out of transit variability because it's a very active star.
Uh-huh.
And also we put priors on the windows around when we expect the TTV midpoints to be so that it can account for the timing variations.
Right. Okay.
So what you see here in figure 8 is the photometry from our Juliet fit. The blue dots are the data,
Mm-hmm.
and in each panel it shows a different instrument. So for the test, it's just a phase folded of all 12 of those transits, and in the other plots are all the ground-based transits.
Mm-hmm. On one side.
Yeah,
Cool.
so the solid black lines that you see are the best fitting transit model that Juliet calculated.
Okay.
And the very interesting part here with the TTVs is the vertical dashed lines are transit midpoints. So the black vertical lines are
Okay.
the expected linear midpoint prediction
Okay.
if we basically didn't consider TTVs. Um, and the red vertical lines are the actual TTV midpoint we observe.
Yes.
So,
Yes.
as you can see in figure or this, the B plot that can range from like a few minutes, or in the C plot that can range to like a couple hours.
Yeah. Yeah.
So that really shows you why we had some trouble in our follow-up initially. The TTV amplitude is about 100 minutes.
Mm-hmm.
Um,
That's also really,
yeah, and I
yeah,
guess
it's really cool. You got it on all these different instruments. So,
I know, yeah, it was
verify.
seeing this visually just clarified things a lot for
Yeah.
us.
Yeah. Very cool. Beautiful plot. Okay.
And then scrolling down, it has the radial velocities from the Juliet fit.
Because it was a joint fit. Right.
Yes.
Right.
So again, the blue dots are the data.
Okay.
Um, on the left, we have the full baseline of the HPF RVs as a function of time. And on the right, we have the phased RVs
Okay.
in both of these plots. The black line is the RV model that we got from Juliet. And the residuals are at the bottom there.
Okay. Those are.
Yeah, so basically, we were able to
Okay.
um, recover an RV semi-amplitude of 14.4 meters per second and get a 4 sigma mass constraint with these
Cool.
Juliet models.
Very
So that
cool.
was really awesome to be able to see for um, TOI 2015. And
Right here. 13.
yeah, if you scroll down, I think then to table 2, it should have all the parameters
Prime.
listed together from this fit.
Very good. Very good.
Yeah, so that's everything we used from the priors that we used in the modeling, and also there's salting posteriors. So
Mhm.
yeah, this gave us a really good handle about kind of the parameters for TOI 2015b. But again, we were seeing this mysterious potential second object that could be causing the TTVs.
Mhm.
Um, in the TLS, we didn't see any additional transits with tests.
Okay.
But what we can do is model using a TTV RV fit to try and test solutions for potential non-transiting companions.
Right. Okay. I'm with you.
Yeah. So, I guess going down to section 4.3 or up, I'm not really sure.
I'm not sure where I lost where. I think it was up because I saw the joint RV fit up here. Yeah. So 4-3.
Yeah. Yeah. So, yeah, this whole section in analysis was done by our amazing contributor, Kento Masuda. He was invaluable in this project in helping us understand the TTVs here.
Great.
Um, basically, what he was working on was helping us find optimal two-planet solutions around common mean motion resonances.
Hmm.
Just to explain what a mean motion resonance is, it's when systems have orbital periods that are related by integer ratios.
Hmm.
It basically happens again because of the gravitational impact of the objects on each other. So you see this often in TTV systems with near mean motion resonances.
Cool.
Um, so here with TOI 2015b, we're favoring a configuration with a non-transiting outer planet. So for this study, we look at a few different potential period ratios,
Yep.
which are 2-1, 3-2, and 4-3.
Okay.
Um,
As smaller as we
and
go.
yeah, I guess you can scroll to table 3 now.
Okay, and then we can do that. Okay, table 3. Rebound is used for the n-body integrations, and table 3. Okay, mean values.
Yeah, so Kento created this package, JN Kepler, in Python. And basically what it does is it models photometry and RV data for multi-planet systems using n-body integration.
Yes.
And it specifically specializes in systems with a large number of parameters and with strong degeneracies. So that's perfect for TOI 2015 because we used 10 free parameters for the sampling process. And there are also strong degeneracies here for the period and transit midpoint of the candidate planet C that we have.
Mm-hmm.
Um, so yeah, basically after integrating these three potential solutions to see if they were stable long term, and that's for like a million years, what I mean by long term.
Yeah, okay, thank you. Million years. Okay.
Ultimately, we adopted the 2-1 solution as the most likely case. So you can see that in the plot
Okay.
here, given these three period ratios. We cannot conclusively exclude the other options
Yeah.
based on just the data we have available to us at the time.
Okay.
So you'll notice that in the 3-2 and 4-3 solutions,
Wow.
we only have the medians and not uncertainties on the posteriors.
Okay.
And that's just because the MC didn't have the convergence needed to get well-defined uncertainties.
I'm with you.
One interesting difference between the 2-1 solution and the 3-2 and 4-3 solutions are that both the 3-2 and 4-3 solutions preferred a larger mass ratio
Okay.
than in the 2-1 solution, and they also both favored a smaller mass for TOI 2015b.
Right.
It characterized it as more of a sub-Neptune.
Right. Mm-hmm.
Yeah, so basically what this shows us is that we need more observations.
I'm- I'll ask about that later. I'll ask about that. Okay.
So these TVs are definitely very challenging. And to be able to nail it down conclusively, we just need more information. So if you scroll down to figure 10,
Figure 10. Let's roll on down. We got some discussion. Figure 10. Yep. There we go. That was the one I really liked. Yeah, 10. Yay. TTVs.
yeah, so this is a plot of the TTVs as a function of time for TOI 2015b
Yes.
um, from Kento's FETs. So basically what this plot is showing you is stable samples of the 2-1 solution in blue, the
Mm-hmm.
3-2 solution in orange, and the 4-3 solution in green.
Okay.
So what's plotted here is 20 stable samples of each of those.
Okay.
The white points are the TTVs from the transits collected in this study.
Yep.
Um, but I guess you see to the right of the white points, things start to get a little messier toward the end.
Indeed.
Yeah, so
Yes.
basically, this is kind of extrapolating into the future about potential solutions. At the time, test sector 78 hadn't been observed, but it has been now.
Okay.
Um,
Okay.
so that would give us more data points.
Oh, you want to
And
scroll?
in the appendix also, we have a table of predicted transit midpoints that can help for people trying to do ground-based transits.
Yeah, and
So
those are a pair of really awesome appendices. I encourage you to check those out.
yeah, that's the transit information. And I guess if you look at figure 11, you'll see the RVs.
Okay, figure 11. Let's see, mass. Okay. we take care of all that. There's our mass loss, Neptune, and there we go. Let's zoom out a little bit to get it all.
Yes.
And
Yeah, so
some likelihood of
yeah,
it.
this is an RV plot of what the 2-1 solution of the joint TTV and RV fits returned.
Yep.
Yeah, here the white circles are the data points, and the blue line is the model from the joint fit. The top panel is the full-time series, and the bottom two panels are phased data. So on the left is TOI 2015, phased to the 2-1 solutions orbital period of 3.35 days.
Yes, thank you.
And then in planet, or in the C plot, we have the outer candidate planet phased by the solution of 6.7 days that the 2-1 solution gives.
Yeah.
So yeah, that's kind of preliminarily what we have for the TTV analysis.
Nice. Very nice.
And I guess digging into the discussions, I think we saw a couple things about mass and composition, probably the best.
We did.
Yeah,
Bulk composition.
some mass and bulk composition. Actually, in figure 12, we have a plot of this.
Okay, let's do figure 12 and very nice.
Yeah. So this is a mass versus radius plot. The black points that you see here are planets around M dwarfs with TTVs.
Okay.
And the faint gray points are planets around M dwarfs that don't have TTVs.
I'm with you.
The blue squares are where our solar system planets are located. And the red is TOI 2015b.
The data point.
Yeah, all the solid curved lines that you see are lines of constant density that indicate different compositions. So like at the extremes you have at the bottom there in purple, the 100% iron world.
Iron ball. Okay.
Yep. And then up top at the green, you have the 100% water world. And then in between, you see several lines with densities that have a composition of a rocky core with a low mass hydrogen helium atmosphere. Yeah, so the cool thing about planets like this is that although the atmosphere makes up a small fraction of the mass, it's actually the main driver of the planet radius.
Yes.
It can puff so yeah, we see. Yeah. With TOI 2015 in red there, it also falls along this same two-layer composition model. So based on a host star of its age, the host is about a couple gigayears old.
Okay.
We would expect TOI 2015V to have a 94% rocky core and a 6% mass fraction for the hydrogen helium envelope.
Nice.
And this makes sense when we look at other similar dwarf planets or M dwarf planets that have TTVs. So I think on this plot you can see AU-MIC-B.
Yes, right here.
And also K2-146B and C.
Right here, these two, yes.
Yeah, these are both planets that have the rocky core and then envelope model.
Okay.
So, yeah, it's consistent with what we see with TOI 2015b.
Cool. Yes. Yes. It's not way off.
And I think the last figure that we have here.
Slide down. Summary, figure 13. Ooh, Neptune deserts. Okay.
So, just to explain a bit about what the Neptune desert is, basically, it's a region of the data in exoplanet parameter space where we see a lack of Neptune-sized planets in short period ranges. So that's periods of less than about 4 days.
Yeah. Okay.
So what this plot shows, on the left, we have a radius period plot. And on the right, we have a radius insolation plot.
Okay.
Both of them are plotting the Neptune desert. So starting with the left,
Yes.
the dashed black line is the Neptune desert boundary.
Mm.
And this is coming from the models in Mazet et al. 2016.
Yes.
And basically the colorful points that you see here are planets with M-dwarf host stars. They're
Yes.
color-coded by insolation.
Mhm.
And the faint gray points in the back are planets with FGK hosts.
Okay.
TOI 2015b is labeled and circled in green here.
Oh.
And in the plot of radius first period space, you see that TOI 2015 does fall within the Neptune desert.
Yes.
So then looking at the right plot, we have the same dashed black line from the Mazet et al. 2016
Yes.
that gives the Neptune desert boundary. And we have also another gray dot dashed line.
Yes.
This is the same boundary but adjusted for an M4 host star.
Okay. Okay.
So again, the colorful points are planets with M-dwarf hosts, although this time it's color-coded by stellar temperature.
Mm-hmm.
And the faint gray points are planets with FGK hosts.
Okay. Wow.
So this time
Wow.
we recognize that using the same Neptune desert model, but plotting it in a different parameter space, now it looks like TOI 2015 falls outside of the black line.
Yeah. Mm-hmm.
One thing we can recognize is that basically the Mazet models were determined primarily based on an FGK sample of stars.
Yes. Yes.
So when we take into account the stellar type and adjust for like a cooler star like an M-dwarf,
Mm-hmm.
we see that the boundary of the Neptune desert shifts, and the dearth of planets is not as deeply pronounced as you would think. So basically, this is just something that shows us and reminds us that we should take the host star type into account, and that it may be helpful to use these radius insolation plots when we're accounting for studies about the Neptune desert.
If there is one.
Yeah,
Eventually. Seems like we're populating that desert here.
exactly.
Okay.
So I think just kind of concluding and summarizing then,
Okay.
I think the summary is up a little bit.
Not too far.
Yeah. So yeah, TOI 2015 is a tricky but super interesting system. TOI 2015b is a warm Neptune. It orbits a nearby M4 star. The host star is pretty young, about a few gigayears old,
Okay.
and it is a very active star that is rapidly rotating with a period of about 8.7 days.
Huh.
The planet that we talk about in this paper is TOI 2015b. It has an orbital period of 3.35 days, a radius about 3 times that of Earth's,
Okay.
and a mass of 16 Earth masses.
Cool.
And based on our values from the joint RV and photometry fits in Juliet, that includes all the ground-based transits, including TESS and all the RVs that we had access to at the time.
Yep.
We believe that there is a composition of a rocky core with a 6% hydrogen helium atmosphere.
Yep. Looks like rock
And then again, the star of the show has been these TTVs we see.
Super great.
B has large TTVs of about an amplitude of 100 minutes over a super period of 430 days.
Cool.
And we think that this is being caused by a non-transiting outer companion planet.
Okay.
In the study, we tested a few different period ratios for the two-planet assumption. That was the 2-1, 3-2, and 4-3 period ratios, and out of them, 2-1 performed best, though we can't conclusively rule out the other two and basically, we really just need more data to pin down these TTVs.
I'll come back to that. Hmm. Cool.
Um, but yeah, I think that's most of everything, except that there's some really interesting stuff to look at in the appendix too.
Yeah,
So
you check those out. We're gonna keep it a mystery for now, but you should check that. Very
yes.
nice. Very nice. Sinclaire, beautiful work. Beautiful.
Thank you, thank you.
And thank you so much for walking us through your very awesome article on TOI 215B. Very cool. Let's see, and you touched on it more than once, so let me go ahead and push on it a little bit. And where do you think we go from here, given the published article? There's more observations, sure, but what kind? Would it help to do anything in the ultraviolet or anything in the infrared? Um, uh, what do you think some of the searches might be on, or what's the results of the searches coming up from Roman on TTV systems, etc. So yeah,
Yeah.
where do we go from here? Or if progress has already been made, you can mention that. So
So actually, progress has been made, which is very exciting. So actually, recently there has been a paper that was released by, I believe it's pronounced Barkawi, et al. 2025.
okay,
And basically they have many more transits and RVs to add to the analysis. And it seems that they favor a 5-3 resonance for the outer planet.
yeah,
So TY 2015C seems a lot more real now.
yeah, yeah. Okay, okay, tentative, but getting there. So
Yeah.
let me go back on that one. Is there anything to be gained from multi-wavelengths? What if we do something in the IR, near IR, ultraviolet, etc.?
Yeah, well, in particular, because it's an M dwarf a star, we
Huh?
really do favor those kind of redder wavelengths.
Yep.
And I think there have been also RV measurements that they might have taken with Maroon X and things like that.
Oh,
So,
okay.
yeah,
Cool. Cool. Well, it'll be really
exciting things.
interesting. Yeah, it'll be really interesting to see this develop over the next couple of years. It'll be uh,
Yes.
uh, nail down B and probably C. So it'll be very exciting. Very good. I predict an awesome thesis. How about that?
Thank you. Appreciate that.
Very good. All right, and that will do, everyone. And I hope this made your astronomy day and your exoplanet day a little bit better. And we will see you on the next one. Bye bye.
Care.